Okay, this is Justin Jones here. I'm not with the rest of my group as I'm posting this early because I'm going to be on a Disneyland trip all this week. Well, it's only partially Disneyland. There's also a wedding, but I don't really care about that. I'm just going to go over this just on my own. So everyone in the group, they'll make another one, and I'm making this one. So let me just go over these questions. So the first one we have Niemann Pick, rare disease disorder. It affects 1 in 150,000. And then there's a few questions associated with it. So what's the frequency of the lowercase d allele? For this, it's very simple, is that you just take the square root, and that's how you're going to get the frequency of the allele itself. Because since this is recessive, there's only so much, because this is recessive, we need both alleles. So it means that some of them are individual, and so they aren't being representative in this 1 out of 150,000. So there's more characters than 1 out of 150,000, and one of the equations given to us, I think it was a Hardy-Weinbach, is how you say it. That's the one that gives us information. So you get the square root of 1 over 150,000, and you get 0.026. And then for B, simple question, what's the frequency of capital D allele? So if we know that little d is this 0.0026, then everything else has to be capital D. So 1 minus 0.0026 gives us 0.9974. So what's the frequency of the DD genotype? So we use that Hardy-Weinberg equation. It's essentially you're going to square this first number, and you're going to square the second number. You're going to add them together, but then you're also going to times these by each other and times by 2. So I drew that out here. So 0.9974 squared, 0.026 squared plus 2 times 0.9974 and 0.0026. Simplify, you get those numbers. If you add them together, you do get 1. So that is going to be the right numbers, which means that these frequencies of the DD genotype are going to be right. So DD is going to have a 0.9948 frequency in the population. And then it's asking what's the frequency of capital D, little d. That's going to be the same thing, 0.00518 or 52, because we wanted 4 decimal places. So that's question 1. Number 2 is just a bunch of fill in the blank. So we did the Hardy-Weinberg, the part that would represent the IB allele. It's going to be Q2, which is the first part of the Hardy-Weinberg equation. But if we're doing the mixed genotype, we need the 2PQ because that's mixing in the 2 genotypes. Okay, so if 1 in 4,000 individuals population have the DiGeorge syndrome, and it's represented, or what is it represented by in the equation? So what we're looking for, let me make sure. Okay, yeah, so DiGeorge syndrome is dominant, and that's the main thing. So we go to that equation, and we're looking for the affected population. Because it's dominant, that means both the p squared and the 2pq, because both of these, the dominant allele is going to be taken over. Question C, this is referring to the same situation. So what's the 399 portions? Let's just the rest. It's the q squared. The type of plumage found in mallard ducks is determined, and you have these ratios. So what's going to be the frequency of the MD? So we learned in the equation, or in the reading, that what you do is you take each of these, or the frequency of the genotype, and you convert them into a B number. So for the most dominant one, you're going to make it B1. That's this MR. For just M, you're going to make it B2, which is the next most dominant, and then MD is going to be the B3. And that's where you're going to get that from. So same question up here. Which one of these is restricted? Restricted is the MR, so we know it's going to be B1. Human C sickle cell anemia, that was a result of an SMP, which is a deletion of a single nucleotide. Monomorphism, that is where a oh gosh, I'm trying to recite this from memory, not just read the question. But no, monomorphism is when you have an entire population where it's effectively just one genotype. Yeah, 99% right there. The other type for local population, that's DEEM, that's simple terminology. Then the major histocompatibility complex, that was saying how our immune system is very, very different, and yeah, highly polymorphic. It just means that you really have to look out for it because humans don't really have the same ones, which is why you have to match organ donors and whatnot. Number 3, Marfan syndrome is an autosomal dominant disorder. For the purposes of this problem, we'll assume that syndrome affects 1 in 6,000. Okay, question is, what is the frequency of the non-disease allele in the human population? Well, let's go back. So Marfan syndrome affects 1 in 6,000. K, is it dominant or recessive? It's dominant, which means that the recessive, we do what we did before. We know that the genotype, or sorry, the phenotype of the non-disease allele is going to be this 5999 over 6,000. Well, we just do what we did before, where you do the square root, because some of them are being masked by the dominant allele. So you bring that through, square root of that. So you bring it out to 9998, square root, 9999163. So very, very close to 1, not quite. So then what's the Marfan syndrome allele frequency? Same thing we did before. Take 1, subtract the recessive rate, and you get the dominant rate. What is the frequency of heterozygous individuals in the population? So this is going to be very similar to what we did before. You use the Hardy-Weinberg, and you're going to take this first number, square it. You're going to take the second number, square it, which I did right there and right there. Then you're going to times these two numbers together and then times them by 2. And you want to simplify at this portion. Check to make sure they equal 1, which they do. So it means that our numbers, they're correct and they match a Hardy-Weinberg, what they say will happen. And we're looking for heterozygous, so that's going to be this middle term. So that much is a heterozygous. And then out of population of 5 million, how many are heterozygous? So really simple. Just take that frequency times by 5 million, you get 832 individuals. Number 4, Jeffrey Minton found 3 genotypes in Glacier Tree, Colorado. Okay. So first things first, we need to find the allele frequency of R2 and R3. So we just need to find the frequency for both of them. We've been doing that. It's been in 2 steps, so now it's only 1. So find the total number of alleles that we have. So we're going to have 135 here for R2, 135 again for R2 because there's 2 R2s, and then 44 from the second one. Add all those together and divide by the total alleles, which I gave here is 380. It's just all of those added together times by 2. So you're going to take the total number of alleles for R2 and divide them by 380. You're going to get this ratio. And you do the same thing for R3. So 44 plus 11 plus 11 for the first and the second R3 respectively. Divide that by 380. Then you get 66 over 380 or 0.17. So now we want to use the chi-square test to see if this is in Hardy-Weinberg equilibrium. So we're going to do the chi-square. You need to use the Hardy-Weinberg first. So plug all that in. So 0.826, plug that in there, 0.173, put that in there, times them by each other and by 2, you get right there. Simplify down to these results, and they do add to 1. And you times it by the expected population, or the total population, 380, and they'll get you the expected population for each genotype. So you take these 3 numbers, times them by 190, and you get these. Now for the chi-square test, you just kind of plug everything in. So you take the, it is expected. So 129 and you're going to subtract the observed, 135, and divide by 135. Same thing again, 54 minus 44 up here, and then divide by 44, and then 5.7 minus 11 divided by 11. Simplify, you get that. Simplify again, you get this. Add them together, 71.73, and the square root gives you 8.469. So there we go, we did the chi test. What does it mean? Well, that's all in question C. So we look at the degrees of freedom are 2 because there are 3 variables. And so we just kind of break that out. So we look at this. If we go to that chart right here, we got, so we need, look at the degrees of freedom for an 8.4. So here's 2. 8.4 is going to be maybe 0.02, something like that. I know it's between 0.05 and 0.01. So let's just assume it's 0.02. That is in this region that we reject the null hypothesis. So we will reject it. And then we're supposed to suggest a reason why it may not be in equilibrium. And my guess is that this probably isn't an isolated population. This is in a valley, and there may just be, even if they are somewhat isolated by their geography, spores and whatnot from other trees further away could be brought over by animals or wind, and that can disrupt this population. So that's what my prediction is, because for Heidi-Weinberg equilibrium, you need to have a closed population, or not closed, but independent or sealed off. I don't remember the exact wording right now. So this one, we're given this chart. These are the different alleles that dogs can have. So we have chinchilla, white with dark eyes. This B one, which is pale gray. I don't get why that's B. And then just plain C for albino. So what is the frequency of the CH, CH, B, and C and CC genotypes? Oh, and you know what? I legitimately did not see the CC, so let me, oops. I'm going to type all this in here while we go, because I want to get this right. So basically what you do for these is you just times the 2 ratios together, or the frequencies. So CH and CH, you times 0.37 by itself, 0.37, you get 0.1369. For B, you're going to times 0.25 by 0.15. For this next one, I legit did not see that, or I missed it. So I'll put it in. So it's 0.15, 0.15. I need a tab. Tab will save me. 0.15. I'm going to equal. Let's just come to Excel. So 0.15 times 0.15. That 0.15, I need a times 15, don't I? Yeah, so it's going to be 0.0225. Yeah, equals 0.0225. Okay. And you know what? I think I also messed up here as I'm looking at it again. Why did I? Oh, that's right. Okay. So the reason why I times this section by 2 is because the C, or the B, so we need a B and a C. So the B can come from the father and the C from the mother, or the mother can give the B and the father give the C. So you have to times that by 2. And that's expressed in the Hardy-Weinberg equation by that timesing in the middle quotient. So among 2,000, how many would you expect to have the gray phenotype yet be heterozygous? So first step here is see which genotypes it are. So gray phenotype, that one was CB, I believe. Yep, pale gray right there. So for it to be heterozygous, the only option we have is CB, and it has to be something else, and it has to be lower. Only C is the only option. So 0.25 times 0.15 from there and there, times that by 2, because it can come from the mother or the father. 0.075 times that by the population of 2,000, you get 150. So we're expecting 150 to be gray and heterozygous. And if we had 5,000, how many would have a white coat with dark eyes and be heterozygous? So that's the CD. So for it to be heterozygous, we could do CD with CB or CD with C. And so what you have to do is find out the ratios for both of them and then add them together. So we're going to do 0.23 times 0.25, 0.23 times 0.15. And look at that, I put it into a nice chart. Times it by 2, because we can get all that. Add them together, 0.115 plus 0.069, which I put here gives us 0.184. Times this population by 5,000, because that's what the, right here, 5,000 dogs. That's what it's expected. And that'll give you a population of 920. Question D, among a population of 15,000, how many would you expect to have CH, B, or CC? So this is really similar to what we had before. You just find out the respective frequencies and add them together. So CH, CB, so 0.37 times 0.25, times that by 2, or CC, which is 0.15, 0.15, and you are going to times it by 1. That's going to give you this. Add them together, and 0.2075 times that by the 15,000, and you get 3,112 and half a dog on average. So those are the answers that I got. I hope my rest of my group does better than me. All right. See you all next week.